So here we're going to find the electric field at the surface of a conductor that happens to be in electrostatic equilibrium. And we're going to use Gauss's law to do that. And so to remind you, Gauss's law is we take the integral to find the flux of the electric field through a closed surface. So two-dimensional. And remember, a closed surface is one that is the surface area of some volume. So it's all the way around some volume. And that is equal to the charge that is enclosed by that surface over epsilon naught. So we've got our conductor. And I'm going to draw just like a really, really big conductor. So we're only looking at a portion of the surface. The conductor is down here. Oh, need a new marker. All right, so this is the conductor. And because it's in equilibrium, the electric field inside is zero, because that's always true of conductors when they're in electrostatic equilibrium. Outside, the electric field is perpendicular. Outside here, so this is outside the conductor, we do know that the electric field is going to be perpendicular to the surface. So pointing off like this. And so this is E outside, and that's only true like really, really close to the surface. Like as soon as you get off the surface, it might bend off into different directions, but I've just like really zoomed in on the surface of this conductor. So I'm drawing all the electric field is completely perpendicular, completely 90 degrees to the surface. Okay, those are the two things we know from the video of the conductors in electrostatic equilibrium, that inside the electric field is zero, and then right outside any electric field that's outside the conductor is perpendicular to the surface. How do we use Gauss's law to find the magnitude of this electric field? Okay, the other thing we know about conductors in equilibrium is all of the charge, if there's any unpaired charge, it's going to be on the surface. So there may be a charged surface density here, and maybe it's different. Maybe there's more charge per area here than there is here, but whatever the charge surface density is, if we want to find the electric field at whatever that charge surface density is, we can use Gauss's law to do that. So here we go. Because we're doing a surface, we're going to do what is called a pillbox for our Gaussian surface. That is the closed surface that we're going to find the flux through. So it's going to have a top, it'll have sides that will extend through into the conductor, and then it will have a bottom. So top, bottom, or top, sides, bottom. And let's go ahead and now do out this integral. We're going to have to do it in three parts. We're going to have to do the surface integral across the top. We're going to have to do the surface integral on the sides here, and we're going to have to do the surface integral at the bottom. Okay, so this guy, flux through my closed surface, I'm going to break up into the flux through these three surfaces that make up my total surface. There's going to be the top, and that will be the electric field that is outside, so this one, because the top of my surface is outside, times this surface area here, so I'm doing the integral there. And then I'm going to do the side here. So I'm going to integrate around this sort of curved side here, the electric field. And unfortunately, the side is both outside the conductor and inside. So this is like both the outside and the inside electric field. But I'm going to dot it with the area. And then finally, I'm going to do the bottom surface, this one down here. And that is completely inside the conductor, so that is the electric field inside, dotted with the area. Okay, now let's do this one by one. This guy, the top, well, it is outside, it's the electric field outside, and the one thing we know about the electric field outside is that it is perpendicular to the surface. So this dot product is just going to be a regular old product because, of course, this dA, remember, the direction of dA is normal to the surface. So on this top surface, it is pointing like that. That's dA. All right, so that's this bit. Let's go to the side now. Well, now dA points off this way, or, if we're over here, off this way. And those two are perpendicular to the electric field, at least on the top. And when they're inside the conductor, there is no electric field. So in either case, this guy's going to be 0. So that whole integral disappears, becomes 0. It's a plus 0. Moved on the side. Okay. Finally, on the bottom, the electric field on the inside of the conductor is also 0, so it really doesn't matter what else is going on here. This whole part is also 0. Okay. So this closed surface is going to have no flux except the flux that is through the very top. So this closed surface integral turns into just an integral of the flux through this top here. And what we're going to do is then we're going to shrink the area down very, very far, and so it will be small enough that the electric field is going to be constant over a tiny enough area here. So we'll be able to put the electric field out of the integral. And you normally can't do this because normally you need to, enclose the surface or keep it out a specific radius. But here, because two of these sides are 0, the flux through the 0, we're allowed to kind of shrink things down to suit our purposes. But do remember that this is now a very, very local equation. It's only true at some teeny tiny little part of the surface right there because we need the electric field to be constant everywhere of this surface. All right, so then this is just an integral of the area. So let's just say whatever this actual area is of my Gaussian surface, let's just call it A. Whatever number it is, we'll give it the symbol A. So now we've done the integral. Okay, so this side of the integral is just the outside electric field times the area of my little Gaussian pillbox. So I'm going to erase that and just replace it with E on the outside times the area of my pillbox. All right, what's going on in this other one? Well, that's a constant, E naught's a constant, so we just need to know how much charge is enclosed by my Gaussian pillbox. Well, it's going to be however much charge is on this sort of circle that mirrors the top of the pillbox. So this also has an area of A, and we have the charge density. And the charge density is the charge divided by the area. So if we multiply the charge density by the area, we get the charge that's enclosed. So I can replace this with A times my charge density. And then I have A on either side. So I can just divide that out. And using Gauss's law in this sort of strange fashion is how we are able to say, okay, the magnitude of the electric field anywhere on the surface is equal to the surface charge density at that location. Remember, we're shrinking stuff here, so it's really only at this particular location. The charge density at that location divided by epsilon naught gives you the strength of the electric field right here. And we already knew that the direction was normal to the surface, so we can just add it in the normal unit vector there.